So now we have the overall mass balance across this perfectly mixed reactor, and I've just reproduced that out here, erased out the derivation for that. So let's just shift that equation up here, and to solve this balance, we need to expand out for this Ra. So concentration of A, that seems to be the variable of this equation. And if we can rewrite Ra in terms of that concentration Ca, then we have made significant progress towards solving for this reactor. So let's look at this Ra. And now we note that in this balance here, this is written in terms of concentration. So that's moles of A per cubic meter of reactor. So this rate here must be moles of A per cubic meter of reactor per second. So this is the volume-based reaction rate. But what we have when we start out is the intrinsic reaction rate, which is Ra double dashed. So that's the rate per area of catalyst particles. So this is moles per second. The units of this is moles per second per area of catalyst. So just to be explicit, let's say per meter squared of catalyst, let's just say dash cat here for catalyst. So that's Ra double dashed, and we'd like to get to Ra, which is the rate that has units of moles per second per cubic meter of reactor. So that's on a per volume of reactor basis. So how do we translate between these two? Well, let's take Ra double dashed, and we can see first of all that if we were able to multiply this rate per area of catalyst with the total area of catalyst in the reactor, then that must be the rate in terms of moles per second. And if you look here, if we know the mass of catalyst in this reactor, and if we know the surface area per mass of catalyst, then we could simply take that surface area. So let's say we have the specific surface area, the area per mass of catalyst particles, then this product here, moles per second per square meter times square meters per kilogram. That product gives us moles per second per kilogram of catalyst. And then if we just multiply by the mass of catalyst here, then we have moles per second of A disappearing in that reactor. That's still not quite what we want. Remember, this is moles per second per cubic meter of reactor, so it's per volume of reactor. So we should divide this through by the reactor volume as well. And then this is equal to the volume-based reaction rate, which is what we want. Right, so that's how we can translate between the area-based rate, or the intrinsic reaction rate, and the reactor volume rate. And that's the starting point for that reactor. So you can see if we can get ourselves to estimate this intrinsic rate, this rate per area of catalyst particles, then we can connect to the overall material balance. This thing is quite familiar to us. So we need to unpack this Ra double dashed. So Ra double dashed, that we can get from the kinetics. So that's normally supplied to us. Let's say it's a first order reaction. We've got some rate constant there, and then we have to multiply with the concentration of A in the particle. Now we note here that these particles, they look innocent enough as they are, but if we expand on those things, we find that those are extremely porous particles, and in fact most of the reaction happens inside the particle. Right, remember, these particles, they may only be microns big, right? Maybe 100 microns is the size of a particle. But the pores, if we magnify a pore here, let's say there's a pore, right, that we're looking at. So here's one of the pores magnified. The molecules actually diffuse into these pores, and then there are active catalyst centers impregnated on the walls here, and so the reaction is actually happening inside these pores here. So the majority of the area is in fact not on the outside of this particle, it's inside the particle, and you can get to crazy numbers. You can get hundreds of square meters of area per gram of catalyst. So most of the reaction is happening inside the particle, and that means that the concentration of A may change across that particle. You can imagine that out here in the fluid, right, if you look here on the reactor, there does exist some concentration of A there. Let's just use a different color. So in here, there's some concentration of A, right, which is what we said there. But near the particle, that concentration might be quite different to the concentration that's in the bulk fluid. So if we look close by the particle, find somewhere around that particle there's some concentration Ca, which is the same as this Ca, namely the concentration in the bulk fluid. But as we get closer to the particle, remember that A is disappearing near that particle, it's reacting away. So inside this particle, the concentration of A we expect to be lower than out here. And there are two layers of mass transfer resistance that the particle might offer. So first of all, we might have difficulty in diffusing to reach the surface of the particle in the first place. So our external mass transfer might play a role. And then once we start diffusing into the particle, right into the pores here, there might be some additional mass transfer resistance. So we eventually don't actually know what concentration applies, right? We'd like to be able to use this expression because we have a nice kinetic rate constant and all we need is a concentration. However, the concentration in the overall mass balance refers to the fluid. So that's the concentration in the fluid, whereas the concentration that applies for the actual reaction is the concentration inside these pores here. So we need to correct for this concentration. We can't say that this concentration in our rate expression is the same as the concentration in the fluid here. So we actually need the particle's concentration. So let's amend this notation. Let's say Ca over bar is the average concentration inside the particle. So there exists some average concentration in this particle that we have to determine before we can solve our reactor balance.